So Chanel, first of all, what do you call this symbol over here? What's that? What is this? What is this called?
A battery.
Yes, a DC battery. Well, all batteries are DC. And what is this squiggly line here?
That's the resistor.
Yes, yeah, yeah. I'll be surprised when students actually watch the video. So, don't mind my surprise. What kind of circuit is this? Series or parallel?
That would be series.
Right, because on the current, there's two types of currents: conventional flow of current and electron flow of current. Do you know how conventional flow of current flows?
Is that the one that you said that runs in one way, like from the positive to the
Yeah, that's it. So positive to negative. The longer terminal is the positive terminal. The shorter terminal is the negative terminal. If there's only one path for current to take, it's a series circuit. And you see that current only takes one path.
Yes, sir.
Great. So if you like, you understand the basics, and if you had this circuit here, what kind of circuit is that, guys?
Parallel.
Yeah, because at this junction over here, you call that junction, and it makes sense. Chanel, have you ever driven before?
Yes, sir.
Check thing. Zachary, have you ever driven before?
Ah, see.
Zachary, come on, man. That's a little to give you a driving practice. But don't feel bad or anything. I only learn how to drive in upper six. Yeah. Alright, yeah, so Chanel. Doesn't it literally look like a junction? Like imagine you're driving on the road and you have two possible different parts over here, so like it's a junction, right? That makes sense, and you understand why we call it a junction?
Yes, sir.
Nice. At this junction, you can either take that part or that part. Current is going to split at that junction. Do you think it's going to split into equal parts, or do you think it'll split depending on what the resistor values are?
Answer.
Good morning, Jaden. Yeah, hearing you, Jaden. Nice. Nice. Finally. Yes. Yeah, so Chanel, do you think the current would split evenly? Or it depends on what the values of the resistors are?
Does it depend, sir?
It does depend. If this is 10 ohms and this is 10 ohms, seeing that both of them have the same value, the current would split evenly. You understand? It would split evenly if it is the same value. Now, do you understand what a resistor does?
Yes, sir.
What does it do?
Basically, it slows down the amount of current would be passing through, kind of.
Well, it slows down the flow of electricity. Um, that's definitely what it does. And you could think of it like it limits the flow of current. Let me explain. If you had a hose of water, right? Imagine you have a hose of water, and this hose is split into two. You with me?
Yes,
So
sir.
water is flowing. Now, everybody in class, if you had a hose of water and you step on this, say put a restriction, where's all the water going to flow out of now? Where is all the water
The
going
other
to?
side.
The other hose, Chanel, that makes sense. Like if you block one of the exits, wouldn't it just go out of the wouldn't more just go out of the other exit?
Yes,
Yeah.
sir.
So it's the same way in a circuit. If you have a parallel circuit and you have a really big resistor, let's just say this is like a 1,000 ohm resistor, and it's like a 1 ohm resistor. Chanel, you know where most of the current gonna go?
The one with the lesser.
Exactly, to go through the 1 ohm resistor. See, now it has a lower resistance. So I feel like you're in an okay position for somebody that just joined in the midst of everything. Good on you for watching the videos. So let's correct the homework. So Zachary's gonna help me with the first question. Fun. Wait, I'm not seeing some people, and I'm concerned. Right? Sheena. One moment. Yeah, me know everybody else is, but we have to continue. Alright, cool. So let's answer this question. So Zachary, they say calculate the reading on the ammeter in milliamps. Guys, do you see this? M, the small m represents milli, the big E represents amps, and current is measured in amps. Proper way to say it, amperes. So that's really milliamperes, but everybody is just saying milliamps. So they want us to find the reading on the ammeter when the switch is open and when the switch is closed. So Zachary, we'll be dealing with the switch open. Okay? Zachary, if a switch is open, can current pass through that threshold, or will it stop before the switch?
Say it won't be able to pass through.
We'll be able to pass through, right? So the switch is open. So let's see what that would look like. Okay, right now, is the switch open or is the switch closed?
The switch closed.
Can everybody in class see that the switch is closed, meaning that there's a path for current to take?
That's good.
Okay, so what I'm going to do is I'm going to break that circuit. Alright, I'll break that circuit. Yeah. Aha, the circuit right now is what?
One.
Say that again?
But the switch open.
Yeah, the switch is open. So, Chanel, imagine the flow of current here, right? Chanel, would the current be able to jump this gap and continue flowing through that node?
No, sir.
Nah, it would not be able to continue flowing and go through that node. So in this node, there's going to be no current. And by the way, guys, if any of you are doing electrical engineering, you will soon learn about a node. So effectively, this is our node, and this is our node. Nodes are measured with respect to ground, and node represents different regions that have varying potential differences. So you'd have a different potential difference before the resistor, and you'd have a different potential difference after the resistor. So, I mean, you guys will learn about nodes if you plan on doing electrical engineering. But anyways, this is our open circuit. So, Zachary, and I could just put a big X over here because no current gonna flow through here.
Yes, sir.
Yeah, no current gonna flow through here, so you can put a big X. No current is flowing through here. So, current flows from positive to negative. That's the conventional flow of current. So let me just draw in the arrows. So Zachary, when the current reaches this junction, is any current going to go through here?
No, sir.
I mean, well, it will want to go here, right? But it can't jump the gap, so it can null and void.
Yes.
Am I going to do this, guys?
No, sir.
Rest of people in class, am I going to draw those arrows going down? Does that make sense?
No.
No, that don't make any sense. Remember, this path is open, so there's no current flowing through flowing through those nodes. None. So let me ask you all a question, Zachary. When the switch is open, does that look like a parallel circuit or a series circuit?
A parallel circuit, sir.
Oh, what make you say that?
So, wait, you say when the switch close or open?
I say open.
Now, when it opens, so it'll be a series.
You sure?
Yes, sir.
Why?
So because the current not gonna be able to pass through the circuit. It wouldn't be able to split because the circuit open since the switch open.
Exactly, the switch is open. How is the current gonna be able to split, right?
Yes, sir.
Um, Vani, can you see that the current will not split since that node is open and the current will be able to jump it on and continue flowing?
Yes, sir.
Yeah, sure. Vani, right? Tell me if you're confused.
No, sir, I understand.
Ryan, Jadon, Chanel, what's going on, guys?
I understand, sir.
And Chanel, what about you? Let me know what's going on.
Yes, sir.
Okay, great. Now, Zachary, if we want to find... Okay, Zachary, I have a question. In a series circuit, at every single point, it's the total current. And why am I saying that? I'm saying that because it's a fixed amount of current flowing through the circuit. So no matter where I put the ammeter, I'm going to measure the same current. You understand that or no?
Yes.
No matter where you put that ammeter, you're gonna get the same reading for current because it's the same current flowing through the circuit. At some parts, you might see current flowing a bit slower. At some part, you might see current flowing a bit faster, or electricity, and that's because of the resistors. But anyway, Zachary, you have to find the total current. Before you could find the total current, you have to find the total what? Remember where I do the circuit. Before you find total current, you have to find total what?
Resistance.
Yeah, you have to find total resistance. You have to combine all the resistors in your circuit. So we have a 2.5k. So I'm going to just simplify it. Yeah, let me know if you all are confused. So we have a 2.5k over there. Then what is going to be following that after that is our what? Gosh man, good notes. What next? What after that?
The 3.6K resistor.
Right, and after that, what next?
The 2.4K resistor.
So Chanel, do you understand that since it's one path that current could take, you can move about the components anywhere?
Sir, could you repeat, please?
Give me a second. Good notes being disturbing. Come on, good notes. Be cooperative. Yeah. So you'd probably notice, Chanel, that the resistor is here, and I put it over here in this instance. That does not matter. It does not matter because there's a fixed path of current to flow, so it does not matter.
Yes, sir.
So, Zachary, any idea as to how we're going to add this? We're going to combine
Yes,
it?
you can just add it normally since it's in series.
Exactly. If resistors are in series, all you had to do, my friend, is just add. That's all you have to do. Just add. So the total resistance RT, which is the total resistance, right, is just going to be the 2.5k plus the 3.6k plus the 2.4k. Guys, do you all understand that k means you have to multiply by? I'm not saying. What does k mean? Somebody tell me. You're gonna multiply by
You
what?
multiply by 1,000, so
You're gonna multiply by 1,000. So just add it up for me and multiply by 1,000. Let me know what you guys get.
8,500.
Did you all get that? 8,500 ohms. Ryan, Jalen, Chanel, Vani, Zachary, let me know.
Yes, sir.
Yes, sir.
Yes, sir.
Sure.
Okay, cool. And the voltage was 12 volts. So let me ask you all a question. If this circuit could be simplified to an equivalent circuit with one big resistor, that is an 8500 ohm resistor, and a voltage of 12 volts, tell me, how would I find the current?
V over R.
Yeah. And that comes from Ohm's law, right? V is equal to IR.
Yes, sir.
It's that simple. Chanel, you good or not?
Yes, sir.
Jadon, Ryan, once you have the total resistance and the potential difference across the whole circuit, so 12 volts here, 8500, then to find I, it's just V over R. And if you're wondering where that comes from, well, V is equal to IR, remember? If I divide both sides by R, I'll get V over R. So my voltage is 12 volts, my resistance is 8500. What's 12 over 8500, guys?
So I get 1.41.
1.41. That's kind of sus.
So I get 1.41.
Okay, I gotta be very careful what you're saying. So when I put it into the calculator, I get 0.001411. Now what does that mean? If I move the decimal places, if I move it just before the first significant figure, I'm gonna see that as 1.41 by 10 to the power 123 minus 3. Now I'm gonna ask you a question. 10 to the power negative 3 is the same thing as what prefix?
Kilo
No.
or milli.
Let me ask you a logical question, Zachary. Does this look big or small? 0.00141.
Small c
So do you think it'll be kilo or milli?
is milli, sir.
Exactly. So that is actually 1.41 milliamps. Let me know if you're confused by that.
No, sir.
Chanel, Vanny, Ryan. Let me know if the math's confusing it there.
No, sir.
No, sir.
Alright, cool. So good. That was the first one. Ryan is gonna help me with the second part of this. So Ryan, in the second part, they're saying that the switch is closed. So if the switch is closed, is the current gonna split at this junction now?
Yes, sir.
Exactly, and that will make it a what type of circuit?
Parallel.
Just parallel or a combination?
A combination.
Yeah. Yeah, it's a combination. You know why I say it's a combination? Let me ask that question, right? Over here, the current is flowing in one path. You with me? Current in one path. Yeah?
Yeah.
But over here, the current splits. So this network over here, that's a what type of network? What is that?
A parallel.
It's a parallel circuit. So when you combine these resistors, you're gonna end up with how much resistors when you combine that?
One.
You're gonna end up with one resistor, and so it'll now look like this. And so by doing that, you'll form a what type of circuit?
Series.
Exactly. Now, upon closer inspection, this sub-circuit here, what is that? Series or parallel?
Series.
Exactly, that's series. So here's my advice for you guys. If you are seeing any series circuitry, simplify that first. Do that. So Chanel, do you understand that the nature of this circuit is both series and parallel?
Yes, sir.
Alright, cool. So Ryan, let's do this thing fast. So Ryan, which two resistors you want to combine first?
2.6 and 2.4.
Yeah, we should do that. Alright, so we got the 2.5k there. If you add 3.6, well, these resistors here, they are in series, right? These two, they are in series. So if I wanted to combine them, that resistance could be what? Resistors in series, that'll be what?
6 ohms.
That'll be 6 kilo ohms, right? Because remember, it's kilo. It's 3.6 kilo and 2.4 kilo. Understand?
Yes, sir.
Right, so my circuit now becomes this. So, on top, that is going to be 6 kilo ohms. $6K. And then this is gonna be what?
2 kilo ohms.
Hello. I fed up a good notes. You know what I mean? What the man that look like Santa Claus was like, I boiling here. I fed up. You know what I'm talking about?
Yes, sir.
Boiling. The white man does look like Santa, yeah. Right, so 6K and 2K. Oh my day. Y'all can't see my face, so y'all can't see the crash out, but so that's good. Yeah. So tell me what to do next, Ryan.
You can add this 6 kilo ohms and 2 kilo ohms.
I don't know why you say it like that. See, like you're combining it. We're gonna combine 66K and the 2K, and the 6K and the 2K in what?
Series.
Yeah. It's in series. I could have swear you say a series, you know. Did you say a series?
Yeah.
The 6K and the 2K. Now let's look at this, Ryan. So the current would split here. So if different currents are going through the 6K and the 2K, does that suggest parallel circuitry or series circuitry?
Parallel.
Right. That's parallel. Are you all okay with that?
Yes, sir.
Right. That is parallel. So tell me, how are we gonna combine that, Ryan? This is clearly parallel, not series. Take your time. How am I gonna combine that?
One over 6 plus 1 over 2 to the power negative.
Let me know what you get for that. Chanel, you have a Sharp or a Casio?
Casio, sir.
Yes! Let's go!
1.5.
Let's go. What you get?
1.5.
And now we 1.5 over what?
Kilo ohms.
Exactly. Wait. I don't think the maths would work. Check out. Let me just verify something quickly. 1 over 6,000. Yeah, that math's not gonna work out. Oh, actually, yeah, it does. Yeah, it does. It's fine. Yeah, it does. 1.5 kilo ohms, right? Can anybody tell me why it's 1.5 kilo ohms and not just 1.5? Anybody?
Because you never changed it to 3,000.
So that again, Jalen?
He never changed it to 1,000. He never multiplied by 1,000.
Well, the reason is because this 1 over 6 represents 1 over 6,000. The 1 over 2 represents 1 over 2,000. And so when you work it out, you had to put the key, right? Because it was 1 over 6,000 plus 1 over 2,000. So it's 1.5
That's what I mean.
thousand. That what you were saying?
Yeah.
Alright. And where's 1.5 key as a number?
1,500.
Right, so that's really 1,500. Are you find like these circuit questions easy or hard? What do you think about them? I find it easy too. Yeah, so Ryan, the circuit now becomes this. So we still have the 2.5k resistor over here. But now the 6k and the 2k are combined into what?
Series.
Yeah. Yeah, you can see that. So we had a 2.5k resistor there, and the 6k and 2k combined to what? What did they combine to?
1.5.
And I just have two resistors in series now, so it's very simple for me to, you know, work it out. Give me a moment. Of course, good notes is rage baiting me. Oh my, come now, man. Why you had to do that? I need to make a compilation of me crashing out over good notes. That would be funny. Yeah, and we mustn't forget that the potential difference was 12 volts. So, Ryan, tell me the last step.
Add 2.5 and 1.
So, the final circuit just comprises of one resistor. And that resistor is going to be how much ohms?
4,000.
That's 4,000 ohms. And the potential difference across the entire circuit is 12 volts. How do I find the current?
V over R.
Right, V over R. The voltage is 12 volts and the resistance is 4,000. What's 12 over 4,000?
V over 1,000.
Say that again?
V over 1,000.
Tell me this a decimal.
Zero 0.003.
So how much milliamps would that be? Alright, so Ryan, if you get 0.003 and you want to write that in standard form, you would take decimal place and you would shift it right before the 3. So place it over there. Now you shift to the decimal place 3 spaces to the what? Ryan?
The right.
The right. So that'll be positive 3 or negative 3.
Positive.
Nah. Think about it. This is the number you had to get back, 0.003. Is that a big number or a small number?
A small number.
A very small number. If you go to multiply 3 by 10 to the power, you know how much 10 to the power 3 is? 10 to the power 3 is 1,000. You multiply 3 by 1,000, will you get back 0.003?
No.
You get 3,000. Yeah, so that don't make sense. So it should really be 10 to what power?
Negative 3.
What prefix is negative 3? Well, I remember all the prefixes. 10 to the power minus 3, what's that?
0.00.
No? Okay, when I say prefix, you know what I mean by that?
Milli.
I mean like milli, kilo, pico, nano, that kind of thing. So 10 to the power negative 3 means milli. So this is 3 milliamps. 10 to the power negative 3 means milli. Guys, are they okay or no?
Yes, sir.
Yes, sir.
Ryan, talk to me. Talk to me, Ryan. Let me know.
Yes, sir.
Ryan, you would make that mistake again, right? When it comes to standard form and prefixes, 10 to the power negative 3 is always milli. I'm gonna if you're ready to move on.
Yes, sir.
Okay. Cool. That's the answer for both questions. I don't think that was that hard. Fanny, you feeling okay with both of the questions?
Yes, sir.
Chanel, what going on with you? Let me know if you're okay.
Yes, sir. I'm okay.
Alright, nice. Jadon, you okay?
Yes, sir.
So Jadon, you are gonna help me with question 6.
Yay.
Ah boy, that's what we want. I like that vibes. Yes, yes, in yay hunting. Let's go.
Yeah, I'm so excited.
Ah,
I can't
look how excited he is.
wait. I can't wait.
Oh my. I just cracked myself up, yes. I can tell the sarcasm, don't worry guys. I don't think he's excited at all. I think I'll realize something like once you become really good in maths and physics and thing, it's like you're looking forward to the question because you're looking forward to get it right. You're looking forward to understanding it and see where you can figure out. It's be fun sometimes. I tell you something. One of the most happiest things you'll be in your life is like when you do a masters and you do some madness, but you know what? You find out after the exam is correct. You'll be so hey, that must feel so happy.
That's a different kind of joy.
Yeah, boy. Like for my engineering maths exam, I most of the paper I just wing it, and turns out it's mathematically correct. Um, I was like, what? Why you figure this thing out? It's crazy. All right, so let me go. Jadon, they're saying calculate the reading on the voltmeter. So, Jadon,
Yes, sir.
guys, you all probably don't know this, right? But across a resistor, there is a voltage drop. Did you all know this or no?
No.
How about the rest of you all? Guys?
Yes, sir.
Okay. Probably wondering why. Well, doesn't the resistor slow down the flow of electricity?
Yeah.
Right. And so what happens is it does that by causing the electrons to collide with each other. So that's why it slows it down. Right? The main reason why it slows down electricity again is because electrons, they give up electrical potential energy by colliding with atoms inside the resistor. That's what slows it down. Think about it like this, guys. If you was driving on a highway and had a big accident, right? End cars would collide with each other, and the flow would reduce. The flow of traffic would reduce.
Yes, sir.
Alright, so Vanny, Chanel, Ryan, Jadon, Kestrel, if you were driving on the highway and had a big accident, cars colliding with other cars, would that restrict the flow of traffic, or would that free up traffic, or what would happen?
It would restrict it.
It would restrict it. Jadon, you understand that?
Yes, sir.
So what I'm saying is, across a resistor, it's slowing the flow of electricity. How? because the electrons give up electrical potential energy. That's the potential energy it has. It gives it up by colliding with atoms inside the resistor. So you have atoms inside the resistor that is kind of it's be like a big accident now, and it's gonna slow down the electrons from flowing through. So what I'm trying to say is, if it gives up electrical potential energy because it colliding with atoms, then there's a voltage drop across the resistor. Why? Let me explain. Before the resistor, is the flow of electricity more or is the flow of electricity less?
More.
Anybody else in class? Before the resistor, is the flow of electricity more or less?
More.
Does anybody else have anything to say? Chanel.
Yes, sir.
So Chanel, the flow of current, is the flow of current faster before the resistor or is it faster after the resistor?
Faster before.
Before. So what you end up with regions that have different rates of electricity. And so what happened here, you have a potential difference developing because of the difference in the flow of electricity. Yeah.
Yes, sir.
So across every resistor you're gonna have a voltage drop. Now let me explain something. And do we know that V is equal to IR?
Yes, sir.
Right? So
Yes,
Jadon,
sir.
if my resistance goes up, then my voltage is going to what? The voltage drop is going to what?
Good job.
And you know what, Jadon, this makes perfect sense, you know. Imagine you drive on the road, right? If it have a huge accident, you feel anybody gonna pass through?
No.
No, so like traffic drop, like everything puts a hold. So same way, if you have a big, really big resistor, all your voltage is going to be dropped across that resistor. You know why? Because not much current will be able to limit the flow of current now.
Yes, sir.
So Zachary, I want to explain that again to you. Ryan, Chanel, Vani, Kestrel, I want to explain that again to you all. Guys, if there's a huge accident on the road, what are you gonna do for the flow of traffic?
Reduce the flow of
Right
traffic.
down.
You're gonna reduce the flow of traffic, so right, where you gonna stop? If you have to stop, would you stop after the traffic or before the traffic?
Before.
Exactly. So here what I was saying earlier. Across every resistor, there's a voltage drop. The bigger the resistor, the bigger the voltage drop. Because they come like more electrons are restricted by the atoms in the resistor. So that's what's happening there. So where would you say there's a greater voltage drop? Across the 1.2k resistor or across the 2.4k resistor?
2.4K resistor.
Exactly. And you can see that relationship from Ohm's law. It says that voltage is directly proportional to resistance, where I is the constant of proportionality. I'm not sure if you're seeing that. If the current remains the same and the resistance goes up, the voltage goes up. You seeing that or no?
Yes, sir.
Yes, sir.
Now there's something called Kirchhoff's voltage law. And it says that the sum of voltage drops across each component in the circuit must be equal to the total potential difference across the circuit. So anybody want to tell me what's the total potential difference across this whole circuit? What's the total potential difference across the entire thing? Tell me, one of you all could figure this out surely. Anybody want to tell me? How we moving so, guys? Okay.
This is 6 volts, huh?
Yes, it's 6 volts. It's 6 volts. Chanel. Doesn't 6 volt... Okay, so 6 volts. That is the potential difference across the whole circuit. You see? Watch. And this is the circuit components here. So 6 volts is across everything. Like, you understand?
Yes, sir.
So Chanel, get what I was saying. The voltage drop here and the voltage drop here. If you add it, what do you think you'll get? What do you think you'd get?
I was going to say the same 6 volts.
Yes. Don't say anything else. You'll get the same 6. Because I was saying just now, Kirchhoff's voltage law. The sum of voltage drops across every single component in a circuit is equal to the source voltage. So, and here what? The component doesn't have to be a resistor. It could be an inductor. It could be a capacitor. You have voltage drops across every single component. Because almost all real world components exist, like they have some sort of resistance. So, guys, you know the thing now. After every component, there's going to be a what? What do you call it? What's the proper name for it? After every component, you'll have a what? Anybody want to tell me? After every component, you'll have a voltage what? A voltage
Meter.
No. Okay, again, if you have real traffic, what happen to the flow of traffic? You got what?
Increase.
You got increase. And you got stop. You don't know where to go. So, try to relate it to this scenario. After every resistor, you'll have a voltage drop. After every resistor, you'll have a voltage drop. A voltage drop, say it with me. So after this resistor, you gonna have a what?
Voltage drop.
Right, and after this resistor, you gonna have another
Voltage drop.
Voltage drop.
Because think about it. Imagine you finally escape the traffic. You gonna bounce up some other traffic. You understand? Yeah. That's what's happening. So here what? Let me show you how to handle a question like this. First things first, we have a voltmeter. Does a voltmeter affect the functionality of a circuit?
No.
No. So, and I'll understand that a voltmeter does not affect the operation of the circuit. It does not. So I'm going to draw that circuit independently of the voltmeter as such. So let's forget that the voltmeter is there for now. We're going to forget it even exists. Okay, is anybody really cooked? If you're really cooked, tell me. Oh, and let me explain something, guys. Can you see that these resistors look a bit different? Yeah or no?
Yeah.
Yes,
Yeah, they look a bit different. This is a fixed resistor, and this is a variable resistor. If, as the name suggests, variable resistor, that means we could do what?
Change it.
Yeah, you could change the resistance. Exactly. But in this instance, they set it to 2.4K. Okay? Now, I don't want to reveal the answer wholesale, but understand something. We want to find the voltage drop across which resistor? Tell me, Jadon.
2.4K.
Exactly. Now, what kind of circuit is this? Series or parallel?
Parallel.
Why is it parallel?
No, series. It don't have no way to split. It's a series.
Exactly, there's no splitting. Watch, positive, negative, right? You tell me if the current ever split.
No, it never split.
It never split. So if it's a series circuit, is the current through each component going to be different, or is it going to be the same amount of current flowing through every single component?
It'll be same flowing.
Exactly. Guys, Zachary, Vani, Chanel, Ryan, Kestrel. Can you all see that it's the exact same amount of current flowing through every single component since it never splits?
Yes, sir.
Yes, sir.
Cool. It never splits. Never. Never. So it's the same amount of current flowing through each component. And that's good. Because the current... I don't want to reveal the answer. Guys, how would I be able to find the voltage drop across this? Let me hear some suggestions. I don't want to reveal the answer. Let me hear you all think. Jiran, if you want to find voltage, does any formula come to mind? Voltage?
V equals IR.
V is equal to IR. You would know V is equal to IR?
Yes, sir.
Now to use this formula V is equal to IR, what two things you need?
Current and resistance.
Yeah, you need current and resistance. Now in this circuit, the total voltage is 6 volts. But let me ask you a question. Are you going to plug in V as 6 or are you actually trying to find for V?
No, we find for V.
Exactly, so we find in for V, right? And to find for V, you need the current and you need the resistance. Which one do you think we could find from that circuit?
Current.
We could definitely find the current. So what do I do if I want to find the current?
V over R.
Yeah, but what are we going to use for the voltage?
6 over 2400.
Nope. I'll wait to correct yourself.
2.4.
Nope.
Add the two resistors.
Exactly. You know why?
No, I don't know why.
Alright. Does this circuit... Let me ask that question. How much resistance does this circuit have?
2.
Exactly. If you tell me to divide by 2.4, you're telling me that the circuit only have one resistor. But that don't make sense. Think about it. This circuit is built with two resistors. You need to combine those resistors first if you want to find total current flowing through all the components. You can't just do it with the 2.4. Let me explain that again. Jadon, in the example we do above,
Yeah.
to find the current going through the circuit, you first had to find the total what?
Resistance.
Exactly. So when you want to find the current here, since it's the same current going through every single component, you have to find the total what first?
Resistance.
Exactly. You have to find the total resistance, and using that you can find the total current. If you say to divide by 2.4 and you tell them it only have a 2.4 resistor in the circuit, but that's a lie. It have a 1.2 as well. What happened into that? So when I combine them, what will I end up with?
3.6.
Right. Chanel, are you okay?
Yes, sir.
You understanding everything so far?
Yes, sir.
Okay, what about the rest of you guys?
Yes.
Yes, sir.
So understand something, with us, with any circuit, chances are you have to find the total resistance before you could find the total current, because you know I is equal to V over R.
Yes, sir.
Gosh, man, good notes playing up. So after today we done with circuits. Right? After this we're going to move on to magnetism. Well, we also have to look at DC, AC diodes, and that shouldn't take long. This is the last set of circuit questions I'm doing. Then we're gonna move on. So I'm gonna move on to direct and AC current. Easy stuff, don't worry, it'll be fine. So yeah, let me finish this fast. So this is 6 volts over here, and this is 3.6 K. Jadon, can you see for yourself that this circuit here can be represented with one single resistor,
Yeah.
and it's only now you can calculate the current?
Yes, sir.
So you again you can't do what you were telling me. So that'll be 6 over what now?
3,600.
What would I get?
Zero 0.0017.
What you get?
0.00166.
Um,
167.
hey, Jaden. Zachary, we catch him, man. We catch him.
Yes.
Gotta put you in our grave. You know what you just now say, Jaden?
What I just now say?
Say it back, say it back.
0.00167.
You didn't catch what you say.
No.
Okay, say back the last two digits.
Oh,
I, I just joking, but yeah, I really don't know what to do with my time.
I'm thinking I have it wrong.
Nah. So it's 1.67 by 10 to the power negative 3. That's what it is. 1.67 by 10 to the power minus 3 amperes. Now, that's the same thing as 1.67 what?
Milliamps.
Yeah, we know the thing, proper. Right. So we know the total current flowing through the circuit, right? So at any point in time, Ollie, how much current is flowing through every single component? Tell me, at any single instance. If you measure the current anywhere in this circuit, what's the current you can measure?
1.67 milliamps.
1.67.
Exactly. So do you know the current now that passes through this?
Yeah.
Yeah, so if you know the current passing through that, you have current, you have resistance, what you gonna do?
High voltage.
Alright, so 1.67 by 10 to the power minus 3, and then multiplying that by the resistance, which is 2.4k, which is 2400. So plug that into the calculator and let me know what you guys get.
$4.008.
Y'all got that? 4.008?
Yes, sir.
Give me an answer to the two decimal places, man. Chanel, give me an answer to the two decimal places.
4.
Two decimal places.
Would be just 4.00.
Yeah. If I ask you for two decimal places, I'll wait till I'm just 4. You had to specify the two decimal places. You had to say, even if it's nothing, you just say 4.00. Right?
Okay, sir.
That's the degree of accuracy. There's a call for that in physics. So 4.00. Now let me show you something cool. Chanel, at the start of the question I asked you, if you add this voltage drop and you add this voltage drop, what are you supposed to get? What are you talking about? Chanel, yeah, tell me, you know. If I add the voltage drop across this and the voltage drop across this, wait, how to give me back?
The 6.
It had to give back 6. So let me see. Here what? I give you only 1 minute. Find the voltage drop across the 1.2k. Do that for me. Find the voltage drop across the 1.2k.
Wait, so
Mm-hmm.
you could just re-explain why the current for the first one is 6/600.
Alright, so this is a series circuit, and what that means is at every single point in that circuit, the same current is flowing through each component. So what I have to do to find the current, I first have to reduce the circuit to its lowest form. So, alright, so let's just backtrack a bit. So Drew, do you understand that this is a series circuit?
Yeah.
If it's a series circuit, then it's the same amount of current flowing through every single component. You understand or no?
Yeah.
So what we need to do first, we need to find the total resistance. So we need to simplify the circuit. So you add these resistors and you end up with this circuit. So we end up with a circuit now that has a voltage and it has a resistance. So if you want to find the total current running through this circuit, you have to combine the components. And remember, okay, if V is equal to IR and you want to find the current going through the circuit, you'll have to divide both sides by R, and it's going to be V over R. The voltage across the resistor is 6 volts, so 6, and it's across the 3600 ohm resistor. So that's how I found the total current flowing through the circuit.
Oh yeah.
Is there any confusion?
I leave mine as 3.6.
Oh, no problem. If you left it as that, then, well, that's fine. It would be 6 over 3.6k. Since it's divided by k, it will be milli anyways. Because if you divide them by k, that is 10 to the power minus 3. Indices and whatnot. Are you okay?
Yes, sir.
Alright. Right. So did you all get the answer for the voltage drop across the 1.2k resistor?
Yes, sir.
Where you go?
2.00.
Okay, anybody else? Vani, Chanel, Vani, and I find I'm not hearing enough of you.
Same answer, sir.
I get 2.0042.
Did everybody get? Vani, tell me, Vani, how would I find the voltage drop across that resistor?
So we'll use V is equal to IR, and I get V in brackets 1.67 by 10 to the power negative 3 close bracket, and then the next open bracket 1200, and then when you multiply it, you get 2.1.
Right. Yes. No, this is the part where I blow the mind. What did I get for the answer?
2.004.
And what did I get for this one?
4.00.
4.0.
Yeah. What's that? 2 plus 4 is?
6.
Let's see that.
Yes, sir.
And I can blow your mind again. This resistance is how much times this? 2.4 is how much times 1.2?
2.
2. And we know that if the resistance increases, what happens to the voltage drop? Guys, if I increase the resistance, what happens to the voltage drop?
It will increase.
It will increase. So if I increase the resistance by 2 times, the voltage increase by 2 times. I'm not sure if all you're seeing that. Watch. 4 is how much times 2?
2 times.
Exactly. And 2.4 is how much times 1.2?
2 times.
Exactly. Already, the question making perfect sense.
Yes,
Yes, sir.
And again, a voltmeter, ammeter, they don't affect the circuit's characteristics. It does not. And I remember of this meme. You know, the African girl, I think she said characteristics. You know what I'm talking about? Oh no.
Yeah.
Yeah, boy. Characteristics. Yeah. Okay. So anytime measuring voltage in a circuit, the voltage is always taken in parallel to a component. Because why? The voltage measures the potential difference across 2 points. So if I wanted to measure the potential difference across the 1.2k resistor, it'd be like this. All you understand?
Yes, sir.
Okay. So I'm gonna have Vani and Chanel help me with 7. My question, Chanel, like, how you know about math vibes? You following the YouTube channel and thing?
Yes, sir.
So you knew about more like, wait, so is it like mom recommended you to the class, like, or you wanted to come to
No,
the class?
sir. I wanted to come.
I see, I see. Nice. I so happy that students want to come to my classes as opposed to parents just forcing them. That's nice, that's nice. Nobody wants to be forced to do something they don't want to do, you know what I mean? Alright, so Chanel, read 7 for me.
The circuit below shows 3 resistors. The resistor Rx has an unknown value. The ammeter has a reading of 3 milliamps. Calculate the value of Rx.
So this question is a bit of a tricky one. Now, before we start, let's just draw the flow of current. Remind me, Chanel, how does the flow of current go?
From positive to negative.
Right, from positive to negative. Yeah? Positive to negative. So Vani, you're gonna answer this question for me. Vani, which resistors are in parallel?
The 1500 and the 1K.
Exactly. Now you probably get into the habit by now. In all instances, we had to do with the circuit. Like in all the examples we do, what do we do with the resistors?
Add them.
Well, we combine them. For you to be able to work on your circuit, you need to be able to find the most simple equivalent circuit. So before we do anything, let's analyze what's happening. That's a good start. So we need to find the unknown resistance. Are you seeing that, right? We don't know what the resistance is, so we have to figure that out. We figured out that these resistors are in parallel. And Vani, when you combine these resistors and they're in parallel, right? It'll just be one resistor. So now you're gonna end up with a what kind of circuit? Tell me, Vani.
Series.
A series, yes. And if you have a series circuit, and how do you find the combined resistance?
R is equal to 1 over R1 plus 1 over R2.
No. In a series circuit, you just simply add, remember?
Oh, yeah.
So guys, by now you all should get into the habit of finding the total resistance. That should be a given. Now, let's reverse engineer the problem. So Chanel, in the question, what is given to us explicitly? Like what things we have for sure?
The battery and the ammeter
So
as well.
say what we have. So we have voltage, so the potential difference. By the way, voltage and potential difference mean the same thing, in case I was confusing earlier. So we have the voltage, check, and we have the total current, check. And we are trying to find R. So we come back to what formula? You have V, you have I, and you need to find for R. What formula do we come back on? What formula has V, I, and R in it?
Ohm's law.
Exactly, we come back to Ohm's law. So V is equal to IR. But in this instance, you want to find for what?
R.
Exactly, so what would R be if you make that the subject of the formula?
V over I.
Yeah. So here what I tell you, at some point in this question, you will have to use our formula. You will have to use V over I. Do you understand?
Yes, sir.
Right. V will be the total potential difference across the whole circuit, so that'll be the battery, as Chanel said. And I, would I be... Look at where the ammeter is. Tell me something, guys. Does that represent the total current or like a piece of the current, a fraction of the current? All you think?
A fraction?
A fraction. Nah. So Chanel, the total current
Yes,
would have
sir.
left the battery. Total current would have left the battery. When the total current reach the junction, the total current is going to split. When the total current, when the split current reaches this junction, they're gonna add back, and it's going to be total current again. So that 3 milliamps is that the total current, or is that like a fraction of the total current?
The total.
Yes, that is the total. If I had placed the ammeter over here, because the current had split, I would get a fraction of the total current. But because the total current merged back over here, it's total current. Do you understand that or no?
Yes, sir.
What about the rest of you all? Do you all understand that this is the total current, not like a fraction of the current?
Yes, sir.
Okay, so Jadon, would this be the total current here, or a fraction of the total current?
A fraction.
A fraction, right? We know the thing. So here what we gonna do. When you're dealing with current and thing, you have to find the total what first? Vanny or Chanel, when you find current in a circuit, you have to find total what first?
Resistance?
Yeah, you have to find total resistance. So let me combine all the resistors now. So I can only leave out the ammeter in my circuit. Remember, the ammeter does not affect the functionality of the circuit, so we can leave it out for now. So this is Rx over here. And guys, how am I gonna combine these resistors here? Okay, by the way, one thing, if it's the, okay, so we have two resistors in parallel, so you could say R subscript P to indicate you're gonna add resistors in parallel. So tell me, what would I do, Vanny or Chanel? How am I going to combine these two resistors, seeing that they're in parallel?
1 over 1500 plus 1 over 1000, all to the power -1.
Chanel, do you understand that or no?
No, sir. Could you explain?
Alright, so this is, anytime you have resistors in parallel, this is the formula I would use to combine the resistors. It's not the derivation for this formula a bit hard to explain right now. But you can't just add the resistors because of what it implies. Like, let me explain. If I have a series circuit, let me explain, right? So Chanel, if you had a series circuit, it comes like you have a hose, right? Imagine you have a hose of water and water flowing. It comes like you press your foot here and you press your foot here. So if I wanted to figure out the total restriction, and I would just add the restrictions on the hose by just, probably adding the forces are pressing on the hose width. Let me run that again. Chanel, if you had a hose with water flowing, right?
Yes, sir.
And you mash here, and you also mash here, isn't there multiple restrictions on the continuous flow of water?
Yes, sir.
So the total restriction logically would just be the sum of this and the sum of this, because the water being blocked by both of those restrictions, yeah?
Yes, sir.
So in a series circuit, real simple, you just add the resistances. Why? Because it's one after the other. Now in a parallel circuit, it's a bit more sus. Watch. So Chanel, imagine you have a 1000 ohm resistor here, and over here you have a 1 ohm resistor. This 1000 ohm resistor, it come like you're mashing the hose real hard. If you're mashing the hose real hard, Chanel, would much water go through there?
No, sir.
So where would most of the water go through?
The 1 ohms.
So think about it, Chanel. The equivalent resistor. Okay, the equivalent resistance would be if you had to approximate it, what do you think the equivalent resistance would be? If you know?
Sir, I'm not sure.
Alright. So you tell me again, Chanel. most of the water will, well, most of the current will flow through the water resistor.
The 1 ohms.
Exactly. So if most of the current flowing through the 1 ohm resistor, what's like the total combined resistance?
1.
Very close to 1 ohm. Yeah. So you understand that, right? You see in
Yes, sir.
1000 ohms over there, and you see in 1 ohm over there, but most of the current going to flow through the 1 ohms anyway. So the equivalent resistance is probably a little higher than 1. So look at that relationship. Intuitively, you're seeing that, you know, the equivalent resistance will be like 1. You know why? Because most of the current flowing through that anyways. So you tell me, you think it makes sense if I want to combine that, I will add 1001?
No, sir.
No. So let's look at the inverse properties. So Chanel, according to Ohm's law, current and current and resistance, they are what proportional? Directly proportional or inversely proportional?
Directly.
Nah, inversely proportional. If you increase your resistance, will more current flow or less current flow?
Less.
Exactly, so you're increasing the resistance, but you're dropping the current. You understand? Like you're reducing the flow of current. I'm gonna that make sense.
Yes, sir.
So, Chanel, an inversely proportional relationship is one that, if one goes up, the other one goes down. So, Chanel, do you understand that if you increase your resistance, you reduce the current?
Yes, sir.
Right, so that's an inverse relationship, which we represent as the reciprocal. So 1000 would really be 1 over 1000. 1 would really be 1 over 1. And that would be to the power negative 1 to reciprocate the sum. Because, let me ask that question. Chanel, the bigger the resistor is that going to allow more current or less current to flow?
More current.
I'll say it again. The bigger the resistor.
Oh, the less.
Less current. So, since the relationship is inversely proportional, I write it as 1 over 1000. Because if the number in the denominator gets bigger, your final answer gets what? Imagine you have a fraction, Chanel. If the denominator increases, what happens to the final answer? Does it get bigger or smaller?
Smaller.
Exactly. And isn't that the relationship we see with our eyes?
Yes, sir.
Think about it. If the resistance gets bigger, the current what? What happens to the current?
The current would decrease.
Exactly. So it'd be 1 over 1000 then. If that makes sense.
Yes, sir.
Like in terms of the relationship, in a parallel circuit, current is going to take the path of least resistance. So, and the relationship between current and resistance is inversely proportional. So that 1000 ohm resistor is going to be 1 over 1000, and that 1 ohm is just 1 over 1. And you add that, you find the sum, and you reciprocate it to get your answer. The proof for that formula is a bit more convoluted, and I can't explain that in full detail now, but I'm just trying to share the intuition. So do you understand? In a parallel circuit, you can't just add like a madman, right?
Yes, sir.
It's a bit more, what's what we're looking for? Can't remember what I wouldn't know. Yeah, I can't remember what I would. That's so weird. I can't remember the word. Anyways, so Chanel, do you understand that in a parallel circuit, the resistances don't add? Because think about it, if you have a really big resistor and a really small resistor, and most of the current is flowing through the small one anyways.
Yes, sir.
So and the combined resistance might just be very small. Watch, let me show you. That example with the 1000 and the 1 ohm, right? Let me show you something. One moment, guys. Yeah, so Chanel, watch. 1 over 1,000 plus 1 over 1 look at that for yourself, Chanel. You seeing that?
Yes, sir.
What you seeing?
That it is equal to 0.10 basically.
You
So it
mean
would
1.0?
decrease.
You mean 1.0?
Yes, sir. Yes, sir.
CSC, this actually sums up what we noticed, and like intuitively, you see most of the current would have flowed through the 1 ohm resistor.
Yes, sir.
So that's why the equivalent resistance would have be close to 1. I mean, some current's still gonna go through the 1,000 ohm, but that's gonna be a very small fraction. So I hope you understand.
Yes, sir.
So anytime you have to combine resistors that are in parallel, this is the formula you use. 1 over the resistor plus 1 over the other resistor to the power negative 1. The purpose of the power negative 1 is to reciprocate the final answer. So like, if I had 1 over 5 to the power minus 1, that's equivalent to 5 over 1. That's what the power negative 1 does. Negative 1 just flips the fraction. You're gonna learn it a bit differently in school, but just use this one. That's my advice. In school, they're gonna tell you 1 over Rp is equal to 1 over R1 plus 1 over R2. And then you gotta add this and you gotta flip it. Don't do that is too much work. Just do this. Easy. Alright, so Vani, when you plug this into your calculator, what are you getting for the combined resistance?
600 ohms.
You're getting 600 ohms. Chanel, can you verify that?
Yes, sir. It's 600.
Bet. Cool. So this is the unknown resistor here, Rx. And we combine the two parallel resistors, and that is now how much ohms?
600.
Right. Chat, we okay so far?
Yes, sir.
Badness. And we know that the voltage is 6 volts, and the current in the circuit is as follows. Is the current. Now, again, in the question, they gave us a reading for the watt current. That 3 milliamps is a reading for what current? What current is that? Chat, what current is that? Is that like a fraction of the current? The whole current was that?
Total current.
Oh,
Exactly. So do you all understand why we are finding the total resistance?
Yes, sir.
I didn't get enough. I didn't answer to give my confidence, right? Guys, if you're finding the total current, you first have to find the total what?
resistance.
Exactly. So we at a very simple stage now. Chanel, as it stands, what kind of circuit is that? Series or parallel?
Series.
This is a series circuit, Vani. Vani, you agree?
Yes, sir.
So Vani, if I were to combine those resistors, we'd have to come up with an algebraic expression. So Vani, this would combine to one. Oh, good note, sir. Hey, you're playing up too much. Yeah, so Vani, when we combine those two resistors, what would the algebraic expression look like?
600 Rx.
600 Rx. So you're saying 600 by Rx? That what you're saying? 600 by Rx?
Wait, 600 plus Rx.
Oh, yes. 600 plus Rx. Are they with me so far? Like, are they confused at this part?
I understand.
Okay, if you are highly confused, these resistors are in what? What are those resistors in?
Series.
They are in series. If two resistors are in series, you simply just do what?
Add.
You just add the resistances. That's all you do. You just add. Do you all understand that? You just add. Guys,
Yes, sir.
Yes, sir.
Zachary, Ryan, you just add, right? Resistors in series, you just add. So,
Yes.
Sir.
I don't know what this is. So I say 600 plus RX. Now, let me just put back the ammeter here. Well, I'll just put the current here. It's 3 milliamps. Okay, so Vani, what we had to find for again?
RX.
So tell me, what we feel we could do next? I simplify the question for you a lot. Tell me what to do next.
You could find the resistance with the 3 milliamps and the voltage.
Explain.
So you could use the formula R is equal to V over I, and you could find out the resistance.
I'll listen. Yeah. You talking good talk. Where's V?
6,
What is the current?
3
3 what?
milliamps.
So that 3 by 10 to the power minus 3, right?
Yes, sir.
Plug that into your calculator and let me know what the total resistance is. Should be like 2000, I think.
Yeah, 2000.
You know how to do that so fast? Vanny, actually you could figure that out too. How do I do that so fast?
Divided.
So again?
Divided.
So yeah, 3 into 3 is 1, 3 to 6 is 2. So you have 2 over 10 to the power minus 3. If you take 10 to the power minus 3 and you bring it up, that goes into what?
Divided. And that will be 2000.
Yeah, you do add maths?
No, sir.
Nah? Okay, anyways. If you take a negative power and you bring it up to the top, it will become a positive power. So that gonna become, well, 2 by 10 to the power 3, which is 2000. That's how I do it fast. So here what? The total resistance, it really supposed to be 2000 ohms. Let me see what you're gonna do now. Ooh, this is the exciting part. What to do? I want to find for RX. What to do?
So you could do the RX plus 600 is equal to 2000.
Hey, Fanny, you make him a proud. I feel like a proud teacher here. Yeah. Because this 2000 ohm here, it really represents the total what?
Total current.
Nah, R.
Oh, sorry, resistance.
This is telling us the total resistance, and didn't we find the total resistance here in terms of RX?
Yes.
Yes, sir.
Yeah, we did. So you know what? They are equivalent to each other. So what next?
Make RX the subject of the formula.
Yes. So 2000 minus 600 is 1400. 1400 what?
Ohms.
Ohms.
Badness. This is a lovely question. So do you all understand any question? Since it gave you the total current and the potential difference, you could have find the total resistance. R is equal to V over I. What's going on here? Guys, if anything confusing y'all, tell me now, you know. Maybe you need to like look at the question and soak it in. Look at it for a bit and soak it in. Alia, if all you're confused, tell me now, you know. Tell me now.
That's very good.
And all in all, you don't have to be scared. If you have any question whatsoever, you just ask me. I try to explain it back so you understand. But I
That's
don't
very
want
good.
do anybody leave here feeling confused. So here what, if I understand so much, I want one all to explain to me how I did the question. Explain the logic. One all give it a chance. Explain the logic for me of the question. Do we have any brave volunteers? Come on, at least one of you guys know this thing. At least one of you could explain this. Jadon, I'm gonna give you the honors. Jadon, try to explain the logic for
I
me.
don't know the honors. Yes, I don't know the honors. I'm okay.
Say that again?
I don't know the honors. I good.
No, try to explain it. Put yourself in an uncomfortable position and you will grow.
But I understand what to do. I just don't know how to explain it.
Well, try to explain it because when you go in the exam and you're looking at this question for the first time, you can't tell yourself, I don't know how to explain it. What
I could
happened?
explain it. I know what to do. I just can't explain it in words.
Try something. Try and better than nothing.
Alright, so first you find the total resistance.
Right, how do that?
You add is a parallel circuit. So you find total resistance. Yeah, 1 over 1500 and 1 over 1000 to get 600 ohms, and that's the total resistance.
Is that the total resistance?
No, that is just for the the current split.
Right. So that's just for that sub circuit. That sub
Yeah,
circuit.
yeah.
Mm-hmm.
Now to find the remaining resistance, you use R equals V over voltage over current.
Wait. You said remaining resistance. It's not remaining resistance. Let me ask that question. This 3 milliamps here. That's the total what?
Current.
And this is the potential difference. So if you use these two, what are you gonna find for the circuit?
Total resistance.
Yes, that is what I want to hear. So if you use that, you're really finding for the total resistance, the numerical answer. So we get 2000. What are we doing with that information?
You take the 2000 and you say 600 plus Rx equals 2000.
But wait, how I know how I get 600 plus RX? How I get that?
Because 600 is the resistance for these the
Sub
parallel,
circuit.
yeah, parallel subcircuit, and Rx is what we trying to calculate.
No, yeah, we're trying to calculate it, right? But RX is in series with the 1500 ohm and the 1 kilo ohm. Well, let me tell you, I want you to develop the vocabulary. So RX is in series with the combination of the parallel resistors. So RX is in series with the combination of the parallel resistors. Say that.
Rx is in series with the combination of what is it?
The resistors in parallel.
Rx is I forget.
Right, so think of the logic. When you combine these resistors here, how much resistors you'll have now if you combine those two, 15 and 1?
1
Right, so that you'll now form a what kind of circuit?
series.
Right, so RX is in what? With the combination of these two.
Rx is in series to the combination of the
The two resistors in?
two resistors in parallel.
Exactly, right? Good. You see, when you put yourself out of your comfort zone, you do little things. As a lesson for your life, right? That applies to more than just physics, you know. But yeah, so Jadon, we had to find the total resistance in terms of Rx. So you combine these two here, you get 600, and then you end up with a circuit. What next?
That's not.
Yeah,
Define the total resistance.
And what's the total resistance in terms of Rx? In terms of Rx.
What I mean.
Okay. I'm not asking you for a numerical answer. I'm asking you for an answer in terms of Rx that has Rx in it. So at this juncture, at this stage,
yeah,
what would the total
600.
resistance be? If you had to come up with an expression for the total resistance, what would you write?
600 plus Rx.
Exactly. So you see that? That's an expression for the total resistance in terms of Rx. Do you know what Rx is?
Not yet.
No, but you write it. You write 600 plus Rx. So you gave me the total resistance in terms of the unknown. What? What's the unknown there?
Resistance.
Exactly. So you gave me the total resistance in terms of Rx. So the total resistance is 600 plus Rx, and that's the expression. Do I know what the numerical answer is for the total resistance?
Yeah.
What's the numerical answer?
400.
Wait, now here I say, right?
No.
This is the expression for the total resistance. What's the numerical answer? What's like the actual answer for the total resistance?
2000 ohms.
Exactly. So if you have this is the expression and this is the answer, you can make an equation and you can solve for Rx.
Yes, sir.
Yeah. This is a nice question. Vani, you okay or no?
Exactly.
Like you sure, like you know you gotta be scared, right? Like if anything confusing you. Come on.
No, sir, and I understand the question.
Chanel, what going on?
I get it, sir.
Okay. So Chanel, you understand that since you give the total current and the voltage, we could have find total resistance 2000 ohms. Yeah?
Yes, sir.
And then we could reduce the circuit to find the total resistance in terms of Rx. So that's 600 plus Rx. And if you had those two, you could find Rx, right? Rx is 1400.
Yes, sir.
Alright. Zachary, I hear from you in a while. Let me know what's going on, Zachary.
Very good.
Alright, bet. So I'm gonna end class a bit early today. I'm gonna emancipate you guys. Alright? Yeah. So I know someone there wants to go beach with all the family and thing. So go organize. Yeah. Later guys. Have a blessed day. Take care everybody.
Thanks,
Be
sir.
safe.
Yes, sir.
Bye.